Hi, this is Chapter 9, Part 5. In this video, we're going to just look at some applications of substitution reactions or examples in synthesis. So this first example that we can see here is a substitution reaction of what's called an acetylide. So you can take an acetylene, shown here, and an acetylene or any alkyne. And if you guys remember from our acids and bases, this hydrogen here is actually fairly acidic. So if you use a strong base like NaNH2, this is actually a stronger base and can deprotonate our hydrogen here. So you're going to end up with the acetylide. And the acetylide is the negative charge on the triple bond here. So both of these shown here are going to be considered to be acetylides. These can undergo an SN2 substitution reaction with primary alkyl bromides, or primary alkyl chlorides will work as well. And this can actually make a longer carbon-carbon chain. This is a very useful reaction for synthesis. Let's look at the mechanism in a little bit more detail. So here's an example. This is another strong base that you can use. You can also use sodium hydride, which will deprotonate our alkyne. So once you've gotten to the acetylide here, and you can see the arrows, the acetylide is going to do the SN2 reaction with a primary alkyl bromide. So it's going to attack at the carbon. The leaving group is going to fall off in our SN2 reaction, and we formed a new carbon-carbon bond. So we've increased the length of our carbon chain here. Another application where this might be useful in synthesis is when you have an intramolecular or intermolecular reaction. An intermolecular reaction is between two different substrates. If you recall, previously we talked about how alcohols can be deprotonated under basic conditions. In this case, the alcohol is getting deprotonated and doing an SN2 reaction with another substrate. So the oxygen is attacking the carbon here, the bromine is coming off, so this is our SN2 reaction. This is going to be a useful application in the synthesis of polymers. As you can see that what we're doing is we're creating a long carbon chain. Depending on the number of carbons here, notice that it just says N. And N is really going to be either a very small number of carbons or a large number of carbons. If you have the situation where you have, we could potentially have formation of a 5 or 6 membered ring, this is going to be favored to do an intramolecular reaction or an internal reaction instead an intermolecular reaction. And you can see here that the oxygen, which is negatively charged, is now attacking itself and kicking out the bromine itself. So the intramolecular situation here where it attacks itself is favored when this is going to be a 5 or 6 membered ring. And we can see this example here on the next slide where you can form a 6 membered ring here. So in this case, the oxygen is kicking out the chlorine. That means that there are 5 carbons in the kind of the chain here. So that N, that N in this case would have to be a 3. And here's a situation where you have 4 carbons. You have a nitrogen attacking and doing an SN2 reaction with an alkyl bromide. This is also working just fine, and you can do that. And then in the previous example, that would make sure that our N would be a 2 in that case. So really, if N is a 3 or a 2, 5 or 6 membered rings are favored. Otherwise, we might end up with an intermolecular reaction where it's not reacting with itself, but reacting with another equivalent. So we've talked a little bit about substitution reactions of alcohols, but let's kind of go over this and make sure that this makes sense. So one of the things to keep in mind is that alcohols are not good leaving groups, right? If they come off, you're going to form a very strong base. So they are going to have to do something else before they can come off. One thing that we do is in acidic conditions, we can protonate alcohols, and we've seen this before, where this is going to act as a base. It's going to pick up a hydrogen here. You're going to end up with a protonated alcohol, which can leave as water. Water is actually a good leaving group, And so in this case, you can see that the bromine is now displacing the water. So this is going to go through a SN2 mechanism when you have a primary substrate here. So the alcohol is going to get protonated, and then the Br minus can attack and kick out the water. And this is going to be a fairly high yielding reaction. And you can see here we have a proton transfer where the alcohol gets protonated. Then once you have a protonated alcohol, the bromine can do a substitution reaction to kick out the water. And so because we have a primary alcohol, this can go through an SN2 mechanism. In the case of a tertiary substrate, the mechanism would be different. So in this case, the alcohol is going to get protonated, fall off as water, and then the tertiary carbocation is going to react with the Cl minus. So you can go, we have this mechanism on the next slide. Here's another example where you have a tertiary substrate. The alcohol is going to get protonated by the HBr. Water is going to fall off. You're going to end up with a tertiary carbocation, and then the Br minus here is going to coordinate and form your product here. So we'll look at an example on this next slide here. So in this case, you can see specifically the proton transfer, where the alcohol is getting protonated by HBr. This is going to give you a Br minus that's floating around in solution. You can see that later this is going to coordinate. The alcohol, or the water now, is going to fall off. So now what you've done is you've made the alcohol, which is normally a bad leaving group, you've turned it into water, which is a good leaving group. So when it falls off, you end up with a tertiary carbocation, and now we have coordination of Br minus with the carbocation to get to our product. One thing that's interesting, and we'll come back to this later, but there is some elimination product that is potentially formed, but in a side reaction, any of that's formed would still form the same product. And so we'll come back to this a little bit later when we talk about these types of reactions. One thing you do have to keep in mind is that any time you have an SN1 reaction of a secondary alcohol, you can potentially have carbocation rearrangement. Your tertiary alcohol here is going to form a nice tertiary carbocation that's stable. But in the case of a secondary alcohol, you are going to end up with a secondary carbocation. And so if you have a situation where it can form a more stable tertiary carbocation, it will do that. In this example here, the alcohol is getting protonated by acid. And you can see here that what we've done is we've turned the alcohol into a good leaving group. It can fall off as water. We have a secondary carbocation now. And the Br minus could potentially come in and react here, but that is only a minor product actually that is observed, because if we have a hydride shift, so you can see this hydrogen here, it can undergo a hydride shift to give you a more stable tertiary carbocation. And if that happens, then the bromine can then coordinate with the tertiary carbocation, or the bromide can coordinate with the tertiary carbocation and give you this major product shown here. So let's draw out that hydride shift really fast. So here, I'll put the hydride in here. So you can see in this situation that the secondary carbocation has this opportunity to do a shift and form a more stable tertiary. So this hydrogen or hydride and all its electrons are going to jump over there, and you are going to end up with the more stable tertiary carbocation. So the take-home message here is that you want to look out for these carbocation rearrangements anytime you have formation of a secondary carbocation, because that tertiary is going to be way more stable. So this is the same thing here. This carbocation is the same thing that is over here, that then can coordinate with the bromine and form the major product.